Welcome back, friends. In this video tutorial we'll be talking about two-dimensional gel electrophoresis, or 2D gel electrophoresis, which is a very important technique to separate proteins out. Now why it is more important than a conventional SDS page, we are going to learn it. Now usually proteins are separated uh, according to their mass or their molecular weight, according to their molecular weight and also their size, right? So using a technique called SDS page or sodium dodecyl sulfate polyacrylamide gel electrophoresis. So conventional method, let me write, conventional method is SD, sorry sir, it must be D. SDS page sodium dodecyl sulfate polyacrylamide, so it is with polyacrylamide gel electrophoresis. Now polyacrylamide is a type of polymer that was chosen to make the gel, that's why it is polyacrylamide gel electrophoresis. Now electrophoresis technique, I hope before going into the discussion, I assume that you must know what is electrophoresis first, and you also know the polyacrylamide gel electrophoresis basics, because I'm not going to talk about the basics of SDS page. I'm going to talk about a speciality of 2D gel over SDS page in this video. For that reason you must understand what is electrophoresis and what is SDS page. If you don't know that, I will recommend you to go in my YouTube channel. You will find a video on SDS page. Two videos are there, basic as well as advanced. You can look those videos, then come here. It will help you to understand what I am telling now. But though I am telling you the basic feature of this electrophoresis, the feature of SDS page, in a gist I am telling you, we are having the gel here, so our polyacrylamide gel, suppose in this case we are having like that. Now we make the grooves like all the other gel electrophoresis system. Now I produce this groove, it is a gel. Now using this SDS page, what is our actual goal? We take proteins, and we take native proteins, right? We take native proteins. Native proteins means we take a protein as it is. We won't denature them, we won't do anything like that. We can take native proteins. Now as we add this SDS onto this protein, so we take native protein and we add SDS, a sodium dodecyl sulfate. Now sodium dodecyl sulfate is a detergent which will denature this protein complex. So ultimately the result is denatured protein. Due to the activity of SDS, the protein get denatured. Now these denatured proteins are tagged with dye or not, they are tagged with dye to visualize them. Then we load them onto this groove. Sorry. The SDS is playing two important roles here. The role of SDS are two different. One of the role of SDS is to denature the protein, and second role is to provide negative charge to the protein, because SDS is providing a lot of negative charge. So to add negative charge to all the proteins. So now what we ensure, that due to the activity of SDS, all the proteins that we got, they are denatured as well as they are marked with negatively charged, or they are coated with negatively charged. Suppose if we take native proteins, we get one protein like that, we get one protein like that. It was extremely difficult for this protein to move through this pore made by polyacrylamide, because this is the cross-linking polymer. It will provide what we call net, like that, after the fixation and cross-linking. So these are the acrylamide polymer. Now these proteins will move through all these networks, but if the protein is not denatured, it is extremely difficult for the protein to move through these pores, right? And also it won't give us the estimate of how the proteins will move. whether it is a large one, a chunk of protein, globular or fibrous, something like that, it will be difficult. For that reason, whatever protein we got, we treat it as SDS to get it denatured, then we put it into this place. Okay, so the actual goal again, all of the proteins are negatively charged. So definitely, as the proteins are negatively charged, they are having a tendency to move towards positively charged. So we'll be putting a positively charged electrode at this point and negative at this point. Okay, and then this protein will move through the place and will get bands of protein according to the need. Now the protein which are shorter in length will migrate longer distance. Okay, and the proteins with large size will migrate lesser distance. Right? That's simple. Okay, this is how the proteins are getting separated using SDS. This is a very basic thing. There are a lot of different things are in SDS page. You can find it in the video. Okay, now this is what is done in SDS page. Okay, but remember, for this region, this separation of protein is based on the size of the protein, right? Based on the weight of the protein and molecular weight and size of the protein, right? So usually that is the important point, based on molecular weight and size of the protein. This is the rule of conventional SDS page, right? So it was beautiful. This technique is really good. We can separate proteins according to the molecular weight. Very fine. We can tag them with dyes and we can elute the protein out. We can make it sequence and everything is very good. But now suppose there are proteins inside cell. Some proteins, many proteins are inside cell which are having same molecular weight. How we can separate protein of same molecular weight using this technique? So how to separate proteins with same molecular weight? There is the biggest question of all. How we can separate them? Now to separate proteins with having the same molecular weight, there are a lot of proteins actually inside our body. How can we separate them? The answer is modification of SDS to two-dimensional SDS page. Because in this case, we are separating the proteins using only one technique, which is the molecular weight. That's why it's called the single dimension gel electrophoresis. But now we can modify this process slightly and we use two parameters to separate proteins instead of one. Now the two parameters are called two dimensions here. One parameter remains as it is, which is the molecular weight, but this becomes a second parameter in this case. But the first parameter in this case becomes isoelectric point of proteins. Here it comes an important topic, isoelectric point. Now what is isoelectric point of a protein? Now remember, what are protein made up with? Proteins made up with amino acid sequences, and the amino acid sequences are of amphoteric molecules like. So proteins are made up with amino acids, and amino acids are amphoteric, right? So as they are amphoteric molecule, they are having both the charges, positive as well as negative, right? Simply, so if I draw the structure, something like that, or I must write it this way. Say this is the structure of a protein, right? Now the amphoteric structure means simply, so this is the amino terminal, this is the carboxy terminal of the protein, right? Now what can happen, this amino acid can be presented in two different ways. One is that it can be presented in this way. On the other hand, it can be it can have three different phase actually. This can have this phase, it can have this phase, it can also have this phase, right? Let's see these three phases. Okay, this basic amino acid chemistry. Now if it is having this phase, so the net charge of the amino acid is, due to this 1 plus, is +1, right? So it's a positively charged. Now if it happens in this condition, the net charge of the amino acid here, it is a negative, so -1, right? Now if both the things occurs at the same time, so the deletion of this hydrogen and also uh, addition of, let's say, addition of one hydrogen here, as a result of both the things are happening together, we are having a +1 for that and a -1 for that. So the net charge of the protein becomes amino acid becomes 0. So one amino acid can be stayed or can be formatted in 3 different ways. One is +1, one is -1, another one is 0, right? The charge, the net charge of amino acid can vary from +1 to -1 to 0. In general cases, if the R group, if we don't consider the R group, if we consider the R group, depending upon the different nature of R group, it will vary, right? But usually it can have 3 different stages. Actually, it can have a positive state, it can have a negative state, it can have a neutral state. That's why it is called amphoteric molecule, right? Now normally what happens, there is a particular pH that governs the charge of this amino acid, right? So pH in which the amino acid is placed in governs the charge of amino acid. That's very important. Now there is a particular pH for all the 20 amino acid sequences at which the charge of the amino acid becomes 0. That is the most important part. So there is a pH at which the charge of the amino acid becomes 0. I must write net charge. So net charge of amino acid becomes 0. There is a pH at which the charge of all the amino acid that we know must have 0. And the pH will vary from amino acid to amino acid, but there is a constant pH for each amino acid. And that pH at which the charge of that amino acid becomes 0, that means the amino acid obtains this kind of conformation, this kind of charge arrangement, is called the pi or isoelectric point. This is also called pi or isoelectric point. So that is the isoelectric point, the pH at which the net charge of the amino acid becomes 0, or it obtains this particular phase, right? This is very, very important. This understanding is very important, and this is the framework for understanding the 2D gel electrophoresis. Okay, so once you know this concept, so this is unique to each amino acid, right? So now we can use these 2 parameters. One is the isoelectric point of amino acid. Second one is the molecular weight of this amino acid or molecular weight of the proteins, right? Now let's consider the proteins. So peptides are nothing but the arrangement of amino acids. So if we know the isoelectric point of each amino acids, we can learn the isoelectric point of a whole peptide, right? So there must be the same. So in this case, first separation of proteins. So there are 2 separation of the protein. Let me write. So there are 2 separation or 2 round of separation. First round of separation is based on pi or isoelectric point, and the second round of separation is based on molecular weight, like the conventional one. This is the new convention onto this old 1D gel electrophoresis. Okay, so now, so what we'll do, if there is a mixture of protein, we'll take all of those proteins. Now first separation will be based on their isoelectric point. So the proteins which are having varying isoelectric point, they will be separated. Then we take it and place it and run the gel via this conventional method, so that the rest of the amino acids are separated by their molecular weight. So 2 way of the separation. Now remember, what advantage this thing can give us? The advantage this 2 dimension can give us is that first round of separation will be strictly based on isoelectric point. And remember, inside a cell, having same molecular weight is common for proteins. But no 2 proteins, I emphasize, no 2 proteins inside the cell can have both isoelectric point as well as molecular weight same. Actually, I can rephrase my term. It is very unlikely to find 2 proteins inside the cell having both isoelectric point as well as molecular weight same. This is very, very rare, right? So we can separate a lot of mixture of protein using this 2D gel electrophoresis. Okay, that's the basic goal. Now let me erase this part and show you how to separate these proteins using 2D gel. Okay, so yes, this is okay. So for this purpose, first separation is based on, so let me write it here, based on pi. So now what we do usually, we take a strip filled with ampholytes, right? So let's say this is a strip filled with ampholyte molecules. So we provide ampholyte. Ampholyte molecules are nothing but small fragment of molecules having distributed charge, some of them positive, negative, and different distributed charge things. Okay, so ampholyte molecules are placed in this strip, so it's filled with ampholyte molecules. Okay, so let me write it is filled with ampholyte molecules. Then what we do, we simply add here sucrose solution and little bit of sucrose solution, and then we add protein spots or protein of our interest there. This is our actual goal, right? We need to separate this protein mixture there. Protein, I must let that mixture, right? So we provide it onto the strip. Okay, now this strip, there are two terminal of the strip. One is the positive terminal, another one is the negative terminal, right? Let's say this is the positive one, this is the negative one. There are two different terminals. Sorry. Now it says the positive terminal is dipped onto phosphoric acid. Okay, phosphoric acid solution, and the negative terminal is dipped onto triethanol amine. Okay, so triethanol amine, and then positive side is dipped into phosphoric acid, negative onto the triethanol amine. Okay, now they are attached to the electrodes. This is positive, this is negative, so you must attach positive and negative electrodes. Now why we are creating all this thing? Now ampholyte molecules are such a molecule, they create a pH gradient through this strip. Try to listen it very carefully. These ampholyte molecules will create a pH gradient through this. For example, let me draw the pH gradient. Let's say from here, it's pH say 1, 2, 3, 4, 5, 6, 7, 8, and so on. It creates a pH gradient, right? It creates a provide a pH gradient, right? So now through this pH gradient, so pH gradient is made by ampholyte molecule. Then we add this protein sequences. Now these peptide sequences will migrate through this ampholyte region. Why at all will migrate? Migrate because of this charge, because we are providing electricity. So we'll force this protein sequence to migrate through this ampholyte string. Now another very important concept about 2D gel, and that is, once a molecule is charged, say a molecule is positively charged. Now let's say we provide three different gradient in a string: positive, neutral, and a negative, right? So this molecule will migrate until it becomes neutral. Can you understand? So a molecule which is a charged molecule will migrate till the point until it becomes neutral. A neutral molecule will have no effect whatever charge, whatever pH we are playing it to it, right? But if a molecule is charged either positive or negative, it should definitely have some effect due to current or pH gradient, right? So this molecule will migrate until and unless it becomes neutral. So let's say here is the molecule. So molecule will move through this positive, so it will move here, it will move here, so still positive charge. When it reaches at this negative point, due to this positive negative interaction, this molecule becomes neutral. So it will stop moving. Whatever current we provide, but still this will not move because it becomes negative. Because it becomes neutral, Neutral molecule will have no effect onto it using electricity on its movement, right? So it will stop there. Similarly, in this case, we are having a lot of gradient, so the protein will migrate from one place to another place until and unless they become neutral. And whenever they become neutral, they just stop migrating there. And when they become neutral, when the charge of a protein or amino acid becomes 0. And when the charge becomes 0 at their isoelectric point, so that is the important point. When they reach their isoelectric point through this pH gradient, they are going to stop there. So if we provide 3 protein mixture here, one protein, suppose it gets there and it migrates up to there, and it provides the isoelectric point 0 here there, and it stops there. Another protein, let's say this green one, it stops here. Another protein, all of these proteins are having same molecular weight, for example, let's say, and the third protein, it stops here. These are the 3 proteins, for example, all of them having same molecular weight, so we can separate these 3 proteins using normal 2D gel. So we take to separate them using isoelectric point. Now due to the presence of this electricity, they will go and move and stop migration when the net charge of the protein becomes 0. So they stop there. So after running this equipment for a long period of time, okay, usually overnight, then we take it out, take this strip out of this place, and we put this strip similarly into this here. We put it into this loading group, because we don't need to load the protein anymore, because the proteins are already there, right? They are already separated in its first dimension, which is their isoelectric point. Now we need to separate these proteins based on their molecular weight. So now we take it and place this strip here. So let me draw this. We take this and we place our strip in this place. So say this is the strip. Let me erase this part. Okay. Now we run them. So we place this strip. Here are the 3 different proteins, the green one and the middle, and here it is, the black one. So now they will migrate, and what they give us? They give us the bands. Actually, in this 2D gel, we don't get the distinct band like that. Instead, what we get is slightly hazy structures like that. I am telling you how exactly we look 3D diagram. If I discuss this using my computer, I will show you the real images. Something look like this, some kind of structure like that. Okay, so you get this kind of bands. Now as the proteins are having same molecular weight, you get the bands at the same region, remember, because if they are having varying molecular weight, we will get the bands in different regions, but we get in the same line. That is suggesting us this all 3 proteins are having same molecular weight, but we cannot separate them using a normal 1D gel. So you need to use this isoelectric point concept to separate them. So now imagine, so like that, there are many proteins inside the cell which are having same molecular weight and cannot be separated if we use conventional SDS page. So for separation, for better separation of the protein extract, we need to rely on 2-dimensional gel electrophoresis, because it is separating using 2 different parameters. First, isoelectric point, second, molecular weight. Okay, so this is the basic process of 2-dimensional gel electrophoresis, and I hope that's helpful. Thank you.